Smelting is a form of extractive metallurgy. Its main use is to produce a base metal from its ore. This includes production of silver, iron, copper, and other base metals from their ores. Smelting makes use of heat and a chemical reducing agent to decompose the ore, driving off other elements as gases or slag and leaving just the metal base behind. The reducing agent is commonly a source of carbon such as coke, or in earlier times charcoal. The carbon removes oxygen from the ore, leaving behind the elemental metal. The carbon is thus oxidized in two stages, producing first carbon monoxide and then carbon dioxide. As most ores are impure, it is often necessary to use flux, such as limestone, to remove the accompanying rock gang as slag. Plants for the electrolytic reduction of aluminium are also generally referred to as aluminium smelters. Process. Smelting involves more than just melting the metal out of its ore. Most ores are a chemical compound of the metal with other elements, such as oxygen, sulfur or carbon and oxygen together. To produce the metal, these compounds have to undergo a chemical reaction. Smelting therefore consists of using suitable reducing substances that will combine with those oxidizing elements to free the metal. Roasting in the case of carbonates and sulfides, a process called roasting, drives out the unwanted carbon or sulfur, leaving an oxide, which can be directly reduced. Roasting is usually carried out in an oxidizing environment. A few practical examples. Malachite, a common ore of copper, is primarily copper carbonate hydroxide Cu22. This mineral undergoes thermal decomposition to 2CuO, CO2, and H2O in several stages between 250 degrees Celsius and 350 degrees Celsius. The carbon dioxide and water are expelled into the atmosphere, leaving copper oxide, which can be directly reduced to copper as described in the following section titled Reduction. Galena, the most common mineral of lead, is primarily lead sulfide. The sulfide is oxidized to a sulfite which thermally decomposes into lead oxide and sulfur dioxide gas. The sulfur dioxide is expelled, and the lead oxide is reduced as below. Reduction is the final, high-temperature step in smelting. It is here that the oxide becomes the elemental metal. A reducing environment pulls the final oxygen atoms from the raw metal. The required temperature varies over a very large range, both in absolute terms and in terms of the melting point of the base metal. A few examples. Iron oxide becomes metallic iron at roughly 1250 degrees Celsius, almost 300 degrees below iron's melting point of 1538 degrees Celsius. Mercuric oxide becomes vaporous mercury near 550 degrees Celsius, almost 600 degrees above mercury's melting point of -38 degrees Celsius. Flux and slag can provide a secondary service after the reduction step is complete. They provide a molten cover on the purified metal, preventing it from coming into contact with oxygen while it is still hot enough to oxidize readily. Fluxes are used in smelting for several purposes, chief among them catalyzing the desired reactions and chemically binding to unwanted impurities or reaction products. Calcium oxide, in the form of lime, was often used for this purpose, since it could react with the carbon dioxide and sulfur dioxide produced during roasting and smelting to keep them out of the working environment. History. Of the 7 metals known in antiquity, only gold occurred regularly in native form in the natural environment. The others, copper, lead, silver, tin, iron and mercury, occur primarily as minerals. Though copper is occasionally found in its native state in commercially significant quantities, these minerals are primarily carbonates, sulfides, or oxides of the metal, mixed with other components such as silica and alumina. Roasting the carbonate and sulfide minerals in air converts them to oxides. The oxides, in turn, are smelted into the metal. Carbon monoxide was the reducing agent of choice for smelting. It is easily produced during the heating process, and as a gas comes into intimate contact with the ore. In the Old World, humans learned to smelt metals in prehistoric times, more than 8,000 years ago. The impact was so pervasive that scholars traditionally divide ancient history into Stone Age, Bronze Age, and Iron Age. In the Americas, pre-Inca civilizations of the Central Andes in Peru had mastered the smelting of copper and silver at least 6 centuries before the first Europeans arrived in the 16th century. Tin and lead in the Old World. The first metals smelted were tin and lead. The earliest known cast lead beads were found in the Catalhoyuk site in Anatolia, and dated from about 6500 BC, but the metal may have been known earlier, since the discovery happened several millennia before the invention of writing. There is no written record about how it was made. However, tin and lead can be smelted by placing the ores in a wood fire, leaving the possibility that the discovery may have occurred by accident. Although lead is a common metal, its discovery had relatively little impact in the ancient world. It is too soft to be used for structural elements or weapons, except for the fact that it is exceptionally dense, making it ideal for sling projectiles. However, being easy to cast and shape, it came to be extensively used in the classical world of ancient Greece and ancient Rome for piping and storage of water. It was also used as a mortar in stone buildings. Tin was much less common than lead and is only marginally harder, and had even less impact by itself. Copper and bronze. After tin and lead, the next metal to be smelted appears to have been copper. How the discovery came about is a matter of much debate. Campfires are about 200 degrees Celsius short of the temperature needed for that, so it has been conjectured that the first smelting of copper may have been achieved in pottery kilns. The development of copper smelting in the Andes, which is believed to have occurred independently of that in the Old World, may have occurred in the same way. The earliest current evidence of copper smelting, dating from between 5500 BC and 5000 BC, has been found in Plotnik and Belovod, Serbia. A mace head found in Kınhasan, Turkey and dated to 5000 BC, once thought to be the oldest evidence, now appears to be hammered native copper. By combining copper with tin or arsenic in the right proportions, one obtains bronze, an alloy which is significantly harder than copper. The first copper-arsenic bronzes date from 4200 BC from Asia Minor. The Inca bronze alloys were also of this type. Arsenic is often an impurity in copper ores, so the discovery could have been made by accident, but eventually arsenic-bearing minerals were intentionally added during smelting. Copper tin bronzes, harder and more durable, were developed around 3200 BC, also in Asia Minor. The process through which the smiths learned to produce copper tin bronzes is once again a mystery. The first such bronzes were probably a lucky accident from tin contamination of copper ores, but by 2000 BC, we know that tin was being mined on purpose for the production of bronze. This is amazing, given that tin is a semi-rare metal, and even a rich cassiterite ore only has 5% tin. Also, it takes special skills to find it and to locate the richer lodes. But whatever steps were taken to learn about tin, these were fully understood by 2000 BC. The discovery of copper and bronze manufacture had a significant impact on the history of the Old World. Metals were hard enough to make weapons that were heavier, stronger, and more resistant to impact-related damage than their wood, bone, or stone equivalents. For several millennia, bronze was the material of choice for weapons such as swords, daggers, battle axes, and spear and arrow points, as well as protective gear such as shields, helmets, greaves, and other body armor. Bronze also supplanted stone, wood, and organic materials in all sorts of tools and household utensils, such as chisels, saws, adzes, nails, blade shears, knives, sewing needles and pins, jugs, cooking pots and cauldrons, mirrors, horse harnesses, and much more. Tin and copper also contributed to the establishment of trade networks spanning large areas of Europe and Asia, and had a major effect on the distribution of wealth among individuals and nations. Early iron smelting. Where and how iron smelting was discovered is widely debated, and remains uncertain due to the significant lack of production finds. Nevertheless, there is some consensus that iron technology originated in the Near East, perhaps in eastern Anatolia, in ancient Egypt, somewhere between the 3rd Intermediate Period and 23rd Dynasty. There are indications of ironworking. Significantly though, no evidence for the smelting of iron from ore has been attested to Egypt in any period. There is a further possibility of iron smelting and working in West Africa by 1200 BC. In addition, very early instances of carbon steel were found to be in production around 2000 years before the present in northwest Tanzania, based on complex preheating principles. These discoveries are significant for the history of metallurgy. Most early processes in Europe and Africa involved smelting iron ore in a bloomery, where the temperature is kept low enough so that the iron does not melt. This produces a spongy mass of iron called a bloom, which then has to be consolidated with a hammer. The earliest evidence to date for the bloomery smelting of iron is found at Tel Hammer, Jordan, and dates to 930 BC. Later iron smelting from the medieval period, the process of direct reduction in bloomeries began to be replaced by an indirect process. In this, a blast furnace was used to make pig iron, which then had to undergo a further process to make forgeable bar iron. Processes for the second stage include fining in a finery forge and, from the Industrial Revolution, puddling. However, both processes are now obsolete, and wrought iron is now hardly made. Instead, mild steel is produced from a Bessemer converter or by other means including smelting reduction processes such as the Corex process. Base metals. The ores of base metals are often sulfides. In recent centuries, reverberatory furnaces have been used. These keep the fuel and the charge being smelted separate. Traditionally these were used for carrying out the first step, formation of two liquids, one an oxide slag containing most of the impurity elements, and the other a sulfide matte containing the valuable metal sulfide and some impurities. Such reverb furnaces are today about 40 meters long, 3 meters high and 10 meters wide. Fuel is burned at one end and the heat melts the dry sulfide concentrates, which are fed through the openings in the roof of the furnace. The slag floats on top of the heavier matte, and is removed and discarded or recycled. The sulfide matte is then sent to the converter. The precise details of the process will vary from one furnace to another depending on the mineralogy of the ore body from which the concentrate originates. While reverberatory furnaces were very good at producing slags containing very little copper, they were relatively energy inefficient and produced a low concentration of sulfur dioxide in their off-gases that made it difficult to capture, and consequently, they have been supplanted by a new generation of copper smelting technologies. More recent furnaces have been designed based upon bath smelting, top jetting, lance smelting, flash smelting and blast furnaces. Some examples of bath smelters include the Naranda furnace, the Izmelt furnace, the Teniente reactor, the Vnukovo smelter and the SKS technology, to name a few. Top jetting lance smelters include the Mitsubishi smelting reactor. Flash smelters account for over 50% of the world's copper smelters. There are many more varieties of smelting processes, including the Kiviset, or smelt, Tamino, EAF, and BF. Bibliography. Pliner. Iron in archaeology. The European bloomery smelters, Prahab, Archaeologiki Ustav Cr. Weltheriges N. H.A. Technical ceramics in early iron smelting. The role of ceramics in the early 1st millennium BC iron production at Tel Hammer, Jordan. In Prudencio, Ideas. and Warenbor, J.C. Understanding People Through Their Pottery. Proceedings of the 7th European Meeting on Ancient Ceramics. Lisboa, Instituto Português de Arqueologia. Welterages N. H.A. and Raren, Th. Iron smelting slag formation at Tel Hammer, Jordan. In Perez Arantegua. Proceedings of the 34th International Symposium on Archaeometry, Zaragoza, 3–7 May 2004. Zaragoza, Institution, Fernando el Católico, EXCMA. Diputación de Zaragoza.